All right, for now, part 6 of today's lecture, we're going to talk about groundwater environmental problems. So the fun, um, so the first step here is going to take a journey out to, so we're going to look at the following graph. This is a chart done by a colleague of mine using global positioning sensors. This is from Rich Journal, but from looking at a noted land surface rise recorded by GPS sensors. So what you see is that from about 2011 through 2012, there, and then 2013, 2014, you see this noticeable rise in the land surface. In particular, in 2014, which was an epic drought. And what you see is that this rise in the land surface parallels very closely the rainfall totals, so that during wet years, the land surface seems to be sinking a little bit. During the dry years, the land surface is rising. What my colleague was witnessing was the actual mass of the groundwater being either added to or, in some cases, taken away from during wet years and dry years, and the land responding isostatically is when you put more mass into that land, it's going to sink a little bit. Then as that mass gets removed through pumping, evapotranspiration, and other processes, the land surface starts to rise. Point being that in 2014 and 2015, we were removing more water from our aquifers in the western parts of the US than was being recharged by rainfall. When that happens, we have a condition called overdraft. All right, let's see how this works now. So we're going to go back to our whiteboard here. So I've constructed a nice little diagram of the aquifer here. Now, I may notice it's missing a couple things, but we got the labels in place. So here we go. You got your confined aquifer, nice little recharge zone to the mountains. You might notice this looks a little familiar from the flyover we did in the previous module here. We're now going to stick a well into the system. So extract a lot of water. And start watering some of these methyl bromide laden strawberries that are so popular here. There we go. And so now that we've done this, we can, as we discover, a cone of depression is going to form in the potentiometric surface. Remember, we have our water table up here. We have our potentiometric surface that's slowly going down like that. That's our potentiometric surface. However, when we start pumping from the well, we get a we suddenly get a cone of depression. A little cone of depression in the water table. The other thing that happens is water starts to reverse flow. So suddenly all that water that had originally been going from left to right in this picture, suddenly a lot more of that's going in there, which means there's a lot less water to go to points downstream. This means things like springs dry up, rivers dry up, and even other wells that are downflow will dry up here. Now, this problem gets a little more dire if downstream of your well you have a body of salt water like the ocean. So typically, because salt water is more dense than fresh water, get this kind of like water intersection between the saltwater zone and the freshwater zone. Is going to look kind of like this. So some saltwater intruding your aquifer, As you continue to pump more and more water out of your aquifer, start pulling in more and more of that salt water. And over time, more and more of that salt water is going to find its way towards your well. And once you start getting salt water going into your well, it's going to be a lot harder to yeah, water your crops. Salt water is going to wreck everything. So we see this in places like Watsonville, California, where we see this whole region is slowly but surely being inundated. And there's actually several areas that are yep. And so there's actually active measures now to try to protect the wells in this area and keep the water flowing to the strawberry fields, but it is not working. Now, the second thing that can happen is as you start moving water, the land surface starts to sink. This is a map of the greater Houston area. Now, if you know anything about the greater Houston area, you know that it is really freaking flat in that part of the world. Like this, it's like LA without mountains. Um, and so that if the land surface starts sinking, you're going to get water popping up in places you might not want. It might even form pools. This was actually one of the reasons that one of several factors contributing to the horrible flooding during Hurricane Harvey during 2017. But we see this not just in Houston, we see this also in Mexico City. Do you see this sort of weird curvy shaped building here? That originally was a horizontal shaped building. The land surface has been sinking. Why is the land surface sinking? Let's head back to our whiteboard. So we think of our aquifers, especially those unconfined or confined aquifers, sort of this being made of lots of granular material here. And there's just a bunch of water between the grains. As you start removing the water, one of the things that holds these grains apart is the water pressure. So as you start removing the water or putting the water in less pressure, all these grains start moving closer together. And when the grains all move closer together and get compacted as the water pressure decreases, land surface above them will start to sink down through a process called subsidence. So a lot of people who built cities like Houston or San Jose thought they were men of substance. But the reality is they're actually men of subsidence. And so we can observe some more. And so we can actually observe some of this from space now. Like this is part of LA. We're seeing the land surface being drawn down in real time as they pump out of the aquifer in that area. So the next part, we're going to focus on cave and karst systems.